Hello, welcome back to EEforEveryone. Today we're going to continue our discussion of electrical ground. If you think electrical ground is always the same potential everywhere, check out our video introducing this concept. Let's see, where did we leave off? Right, ground potential not being the same in two places. Today, we'll talk about a few ways to protect the 5-volt tolerant input to the microcontroller we were talking about in our previous video. When I began to think about ways to safely translate the higher voltage down to a level safe for this microcontroller, I noticed some similarities to logic level shifting circuits. Ultimately, the difference between a logic level shifting circuit and a more typical isolation scheme is how much protection is achieved from the higher voltage being applied to the input and what's actually exposed to the microcontroller. The better isolation you have, the less of that energy is able to get to the system we're trying to protect. So I was thinking about the problem we're facing, taking a 5-volt peak-to-peak signal with a DC offset and removing that DC offset. Ethernet comes to mind pretty quickly. Ethernet uses isolation transformers to protect each side of the interface from the other, and it works really well. Electrical isolation from one side to the other shields the system from potentially huge differences in DC offset because there's no direct electrical connection to the transmitter and receiver side of the circuit. Ethernet isn't a perfect example of what we're trying to do here, since we're working with a single-ended signal and it's built for differential signals, but we can use the same principle to allow a signal to pass through while protecting each side of the circuit from the other. Continuing down my train of thought, optocouplers also came to mind because they're often used when crossing isolation barriers, for example, an enable signal for an isolated power supply. Sometimes a single capacitor can provide enough protection on its own, depending on what you need. In our previous discussion of ground, we used a model that contained many redundant voltage sources and redundant resistances. This model we're going to use today is electrically the same, but looks a little different since we're talking about 4 different systems at the same time, and I wanted to shrink it down a little. I have 4 approaches to share with you, and each approach provides a different level of protection for our microcontroller. 2 are more useful for low-frequency signals, and the other 2 are more useful for high-frequency signals. 2 of these approaches provide significantly better isolation than the other 2. Which approach is better for your situation will depend on a few factors. I think it's also fair to say that these approaches are highly simplified and are not perfect by any means. They're simplified examples that are demonstrating the effect of a component and how it will block the DC offset while allowing the signal to pass through. If I were to implement these into a real design, I would need to modify it to make it work properly, but that depends on the speed of the signal we're trying to pass through the isolation boundary and what we're trying to accomplish. The 4 example implementations I think will serve as a good starting point for our discussion, and 3 of the approaches even works. The 4th looks like it could work and is useful for logic level shifting, but it didn't work when I tried to implement it as an isolation scheme. Well, 1, because it's not isolated at all, and 2, because I didn't realize something about the signal when I was thinking about the problem. I thought I'd leave it in even though it didn't work, and maybe you'll learn something too. Let's start with what's common to all these examples. First, the input is swinging from 0 to 5 volts with a 10-volt difference in the ground potential between transmitter and receiver. There's 100 ohms of impedance from the transmitter to receiver on both wires, and the protection circuitry is placed on the receiver side. There's a voltage source on the receiver side that's supplying a voltage for the receiving circuitry. Fourth, we are attempting to bring information through the protection circuitry such that it can be easily reconstructed on the receiver side. With that out of the way, let's work our way through the list and talk about the differences between these 4 circuits. Optocouplers are great. They achieve electrical isolation from the LED side to the phototransistor side, and there's only light traveling between the 2 sides, so there's electrical isolation achieved. The transistor turns on when the LED is shining. We have a current limiting resistor on the LED side of this optocoupler, which will limit the current going through that diode and prevent damage to it. When this voltage turns off, The LED doesn't see any voltage, produces no light, and the transistor turns off. When this transistor is off, the input to the microcontroller will be 5 volts due to this pull-up resistor. This action inverts the signal. That is, a 1 becomes a 0, but this can be rectified. This approach works like a charm and provides excellent isolation. Depending on the optocoupler chosen, this could withstand 1,000 volts of difference between the output and input side of this device. That is also kind of how a fiber optic system could work. The main difference is that the LED would be a laser, and that'd be on the output side of the circuit, with a fiber optic cable carrying the photons of light from the transmitter to the receiver, instead of a copper cable carrying electrons. Then a photosensitive device would translate that light signal into an electrical signal so that it can be processed. Unlike a fiber optic system, optocouplers switch pretty slowly, and that makes them less useful for high-speed signals or digital communication. Let's run the simulation. Here's some of the signals in this system. First, we have the output of our microcontroller varying from 0 to 5 volts, the ground offset, and here's how the signal looks. Periodic, varying from 10 to 15 volts. This signal passes through the optocoupler, sending bursts of current through the LED whenever there's a logic 1, and those bursts of current in turn cause the voltage on the output to vary. You can see that it is inverted, where the input, shown in blue, is the opposite state of the output, shown in yellow. Notice how the edges of the signal are attenuated quite a bit. They're not a very sharp transition. They're rounded. What this means is that we're spending more time in the transition period, which is distorting the signal. This distortion will eventually cause the logic level of the signal to be incorrect if we try to push a signal that has too high of a frequency through the optocoupler. Now let's talk about magnetic isolation. When using magnetic isolation, low-frequency signals would cause the inductor to appear like a short circuit, and energy wouldn't be transferred across the transformer. That's why the period of the signal was shrunk by a factor of 1,000 for this setup, or the signal is oscillating 1,000 times as fast. The signal on the receiving side of the transformer doesn't look too great, so it can't be directly fed into our microcontroller. Therefore, we've used a comparator to reconstruct the signal and make it a little cleaner. The key thing here is that there isn't a direct electrical connection from the input to the output, just like with the optocoupler. Instead, the changing signal causes a changing magnetic flux, which causes a voltage to appear on the other side. Let's take a look at some of these signals. Again, we can see the input varying from 10 to 15 volts due to this ground offset. This is causing current to build and collapse in the inductor. Notice how there's no direct conduction path for ground currents, so the current through these resistors and on the transmit side is limited only by the impedance of this magnetic isolation and the copper cable. So when we take a look at what we receive, you can see that it doesn't look too great. There are peaks and valleys that align with the logic level transitions, but that doesn't look like a very clean digital signal, and that's just not great at all. But what happens is whenever this input to the comparator is higher than this one, it will output a logic level 1, and vice versa. So by comparing these two inputs, we can determine when it's supposed to be logic level 1 and when it's supposed to be a logic level 0. Let's take a look at that signal. Look at that. It's almost a perfect reconstruction of what we intended to send, but now there is isolation from the transmit and receive side. If I were to implement this circuit in a real design, I would add protection to prevent this inductor from producing voltages that could damage the comparator. However, Our single-ended signal has crossed over the isolation boundary and is reconstructed on the receiver side. Great. This leads us to capacitive isolation. The system also requires higher frequency signals to operate correctly, but to a lesser extent than with magnetic isolation. In this case, when one side of the capacitor, C1, is raised in potential by 5 volts when this starts outputting a signal, the other side of the capacitor is raised by 5 volts as well, and then discharged through R1. So without a termination resistor R1, this voltage would be floating about, it would end up as an average between a potential and a different potential, but that might not align well with the logic levels the microcontroller wants to see. Therefore, we've tied this to halfway between logic level 1 and logic level 0, so as the capacitor is tugging current in and out and applying a voltage potential, it will be centered around the midway point of the logic region. Since our signal has 50% duty cycle, this means that should be centered around 2.5 volts, and since our peak-to-peak swing is 5 volts, it should give us pretty good plus 5 volt to 0 volt varying signal when we're outputting a 10 to 15 volt signal on the transmit side. So this allows a mostly unchanged signal through to the receiver side, but again, I'd add some clamping diodes to make sure that we aren't damaging the input to the microcontroller, since that protection isn't guaranteed by design if a 10 volt peak-to-peak signal were applied, for example. The thing to remember here is that this system only provides isolation to the extent that the capacitors can withstand. If too much voltage is applied, like a few kilovolts, the capacitors would break down and conduct. Therefore, this method isn't a great method for level shifting or isolation unless you know what is going to be on both sides of the system, like 2 circuits on the same circuit board. In this specific case, with everything laid out the way we have here, it's going to work just fine. But reconstructing the signal on the output would be a good idea just to make the data a little bit cleaner and ensure that we won't be violating anything with the input to the microcontroller. Again, we can see the square wave output. And now here's the input. You can see it's not perfect, as we described, but the logic levels are pretty much there, and it goes a little bit above 5 and a little bit below 0, but not enough that it would really damage anything. So reconstructing the signal would make it a much cleaner 5 volt peak-to-peak signal, but depending on your application, this could be good enough. This leaves us with the BJT unidirectional level shifter. When current is passed into the base of the transistor, it conducts. While it's conducting, it's pulling the voltage applied to the microcontroller input pin down to ground. When there's no current flowing into the base, then this is 5 volts. This action inverts the logic signal such that when voltage is applied here at the output, it results in 0 volts being applied to the input. This could be corrected in hardware with an inverter or in software by simply reversing the logic state where something happens. This system has a few big drawbacks. First, the return potentials on the transmit and receive sides are not isolated from one another and both reference to ground, so there's a relatively large current flowing in the ground conductor of the cable. Second, with respect to grounding the transistor, there's always a voltage applied and a current through the base, so what we get at the input of the microcontroller is an analog representation of the signal, but it doesn't meet the logic level of the microcontroller, so we'd need to use a comparator or something else to reconstruct the signal. Lastly, there is no isolation on the ground or data signal, so this just isn't the right solution to our problem. Now, if we wanted to shift the logic level of a reasonably slow frequency signal, and the ground was the same potential on both sides of the system, this level shifter would be more useful, mainly because it's so cheap. There's multiple ways to solve this problem of level shifting, so we won't dive too deep into this. This is just one way that you could use a BJT to invert the signal and also shift the logic level. Once again, we see the 10 to 15 volt square wave and the resulting varying current from about 1 to 1.5 milliamps. This results in a voltage at the input of the microcontroller varying from 10.4 to 11.4 milliamps, which, I mean, there's a signal here, but compared to the 5 volt input, it's minuscule. It would always read a logic 0. So it's not really doing what we intended for it to do, but it could be useful under different circumstances. There are a lot of ways to implement circuit protection and logic shifting, but when mitigating potential DC offsets in systems or achieving a level of isolation between two systems, optical and magnetic isolation are by far and away the two most common and effective methods I have seen. The implementation in real designs is certainly different than what I've showed you today, but the principles at play are very similar. Capacitive isolation is also used sometimes to remove a DC offset on a single-ended signal for circuits like a common emitter amplifier. But this is more common when the maximum voltage applied across the capacitor is both known and well defined. If you think that isolation and level shifting is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!